Hello, welcome again to the lecture series on engineering thermodynamics. Today's topic will be available and unavailable energy. The outcomes of this session will be explain available energy and unavailable energy, define exergy and energy, explain availability, irreversibility, and define second law efficiency. Now let us talk about what is available and unavailable energy. Let us consider an engine, a reversible engine, heat engine, and it is working in a cycle. It's drawing a heat Q1 from a source at T1 and rejecting heat Q2 to a source at T2. Okay. So now the question is, this is a reversible engine. The work done by this engine, according to first law of thermodynamics, W is equal to, since it is a reversible engine, it is maximum work, that is equal to Q1 minus Q2. W maximum. I am using the word maximum because it's a reversible engine. And the work done by that is Q1 minus Q2. So this has been converted to work. This I call it as available energy. Now Q2 amount of heat is rejected to a sink. This is not getting converted into work. So this I call it as unavailable energy. Available energy, unavailable energy. Let us say a system executing a thermodynamic cycle like this on a TS coordinates I have drawn. Okay, process 1 to 2, 2 to 3, 3 to 4, 4 to 1. Let us assume during this process the heat is supplied. So the total heat that has been supplied is area under this curve, as I explained earlier. Area under this curve. Correct? So these two are adiabatic processes. So during this process I have supplied the heat. So total heat that I have supplied to this engine is area under this curve. Probably you can draw like this. This is the total area. Okay. Then during this process, let us assume the heat has been rejected. That is this area. So the heat that has been converted to work is this much. This I call it as available energy. And this I call it as unavailable energy. So that part of the low grade energy, heat is a low grade energy, which is available for conversion, is referred to as conversion into what? Conversion into work. Available for conversion is referred to as available energy, while the part which according to the second law must be rejected is known as unavailable energy. Just let me use the word available energy and unavailable energy. Okay. Right. Now, I'll extend this concept now. Let us draw Carnot cycle. TS. On a PV diagram, if you draw Carnot cycle, let us say 1 to 2 reversible adiabatic, reversible isothermal expansion during which heat is added. 2 to 3 reversible adiabatic expansion. You will get the work, but no heat interaction. Again 3 to 4 reversible reversible isothermal compression during which heat is rejected. And 4 to 1 reversible adiabatic compression during which work is supplied. So process 1 to 2 is reversible isothermal expansion. On these coordinates, the temperature must be constant. So it is 1 to 2. 2 to 3, entropy is constant. 3 to 4, again temperature is constant. 4 to 1, entropy is constant. Okay. Okay. Now, during this process, heat is supplied. During this process, work is done. During this process, heat is rejected. During this process, work is supplied. Negative work. What is the total heat supplied? Area under 1 to 2. What is that area under 1 to 2? Is this. Okay. What is the heat rejected? Area under 3 to 4. This much. So that means what is the heat that has been converted into work? Is this. Q1 minus Q2. This is available energy. This is unavailable energy. Okay, this I am not able to convert into work. Okay, so the maximum work output obtained from a certain heat input. Now I'll use the word maximum work output, that we will see. Okay, obtainable from a certain heat input in a cyclic heat engine is called available energy. So far whatever I said, don't know. It is a reversible one. Whether it is maximum is the question. So what do we do now? Suppose, let us say this expansion process 1 to 2 and 2 to 3. Suppose I have let us say piston and cylinder system. Okay, this is a piston, this is the system. Let us say this system is at pressure P1 and temperature T1. Now we'll go on moving the piston. So on this side of the piston, let us assume there is atmospheric pressure acting. This way. This side the pressure P1, this is P atmosphere. Let us assume that way. So P atmospheric pressure is, let us say 1.01325 bar. And let us say this pressure is something like 10 bar. So this is 10 bar, this is 1.01325 bar. Because of this pressure difference, the piston will start moving towards right. It goes on moving till pressure on either side of the piston becomes same 1 atmosphere. Correct? Then it reaches to an equilibrium position. It cannot move further. So that time, these conditions will be same as atmospheric conditions. Let us say I can call it as P naught and the temperature is T naught. Now you cannot move at all further. That is what we are saying. This system has achieved some kind of an equilibrium with its surroundings. Something we say the system has reached to a dead state. Dead state. Dead state. So the time maximum amount of work, if it is a reversible engine, and whatever work that we get is the maximum work. Let us say in this diagram, let me put this way. Suppose in this, heat is supplied, this rejection point, let us say this was initially assumed that it was rejecting heat at 400 K. Now I will expand this process so that I'll go on bringing it to something like up to 300 K, which is atmospheric pressure. So maximum expansion has happened till it has reached that atmospheric condition, atmospheric pressure and atmospheric temperature. Then you can observe here, this area definitely is the maximum. So this is a maximum available energy. If you want to further maximize, probably the surrounding condition itself you have to reduce. Assume it is 300 K and 1 atmosphere pressure. If I can reduce this to, let us say, 0.5 atmosphere pressure, then I can further expand it. So that's what we do in a steam power plant. We keep the pressure of the condenser very much below the atmospheric pressure, so you can expand it and you can obtain the maximum possible work. You can utilize the complete potential. Anyway, so in a normal condition, maximum that we can expand is to the dead condition, dead state. That is atmospheric pressure. We can represent the temperature as T naught and we can represent the corresponding pressure as P naught, and this state we call it as dead state, DEAD, dead state, and we represent by this suffix. Then whatever work that you are going to get, if it is a reversible engine, it is maximum work. Call that maximum work as availability. Availability. It is a maximum available energy. So the maximum work output obtained from a certain heat input in a cyclic heat engine is called available energy, or the available part of the energy supplied. The minimum energy that has to be rejected to the sink by the second law is called unavailable energy. Unavailable part of the energy supplied. That's the kind of a thing. Later you call that as the availability, unavailability. As I mentioned, when the system is in equilibrium with the surroundings, system will have minimum potential. Such a state is known as dead state, and the properties will have suffix 0. That's what you can go on expanding till it reaches the dead state. There's a maximum expansion possible. Dead state is the state at which system remains in complete equilibrium with the surroundings. There won't be finite driving potential, either thermal potential or mechanical potential, for change to occur. Dead state implies that system is stable and uniform in composition. Its pressure and temperature are equal to surroundings. The system has zero velocity and minimum potential. That state we call it as dead state. So now we'll find out this maximum work. So consider the heat engine, reversible heat engine. Source temperature is T1. Sink temperature is T2. This is T1. It is producing maximum work. Efficiency of a reversible engine is given by this. So you want to make this efficiency to be maximum. This T2 should become T0. So T0 by T1, this value becomes minimum and the efficiency will become maximum. Now corresponding work what? W max by Q is also known as efficiency. This is equal to 1 minus T0 by T1. So now W max can be written as 1 minus T0 by T1 into Q1. That is the maximum work. Now we will find out the maximum work value. So maximum work value. Right. So see here. Consider this process XY. Okay, this is a cycle, right? Right. Let us find out maximum work. Consider the small infinitesimal amount of heat supplied, infinitesimal length of process that the system has executed. So this I can write it as this temperature, his heat supplied is delta Q1. That corresponding temperature is called T1. Then I reject the heat at temperature T0. So efficiency of reversible engine is T1 minus T0 by T1. However, this is the maximum, this is the dead state. So this efficiency is maximum. And the heat supply delta Q1, if I multiply, I'll get the maximum work. Correct. Now if I divide this T1 by T1 is 1, you will get 1 minus T0 divided by T1 multiplied by delta Q1. If I write, I'll get delta Q1 T naught by T1 delta Q1. This is W maximum, so you call this as available energy. So total work integrated, you will be getting total heat supplied during the process X to Y, correct, minus, if I integrate this one, here like delta Q1 is there, so delta QXY will be there. So I written delta XY, T naught and T1 I'll take out, correct, suppose if I take out T naught outside, and delta Q1 by T1 is nothing but change in entropy according to entropy definition. So that is Sy minus Sx. So this T naught you take out, then delta Q by T by definition is entropy change. So integrate it, you will get Sy minus Sx. So W max is equal to Qxy, heat supplied, minus T naught Sy minus Sx. Okay, now heat supplied minus the maximum work that you have obtained, the remaining is what? Heat that has been rejected. That is what you can call it as unavailable energy. So you can calculate unavailable energy using this equation, correct, and maximum work is this. Okay, right? Now we'll talk about what is this maximum work. How do we determine this maximum work? So we will take Carnot engine, a reversible engine. Let us say heat is supplied to this engine QH from a reservoir at temperature TH. Heat is supplied reversibly. Heat is rejected again reversibly. So this is the Carnot cycle. You will get this 1, 2, 3, 4, which I have explained, and the area 1, 2, 3, B, A, 4, 1 is the total heat supplied. Area 4, 3, 4, A, B is the heat rejected at dead conditions. This is the available energy, or you can call it as availability. This you call it as unavailable energy. Unavailable energy. So maximum work is QH minus QL, that is area 1, 2, 3, 4, 1. You call it as availability or maximum amount of work done, and the real one is unavailability. We'll calculate maximum amount of work done. There is. Now let us discuss the concept of irreversibility. See, it is the difference between the maximum work and the actual work. So what exactly it means? So let me put this way. Same Carnot cycle. Let us put this way. This is, let us say, T1, and let us say this one T0, and you have got maximum work, correct, and this is all reversible engine. In actual engine, heat is, let us say, not supplied reversibly. Moreover, there will be internal irreversibilities, and heat is not rejected T naught, something the heat rejected is this much. In this case, in an actual engine, this is the heat rejected. Sorry, in a reversible engine, this is the heat rejected. In an actual engine, this is the heat rejected. Here, assuming this area and this area is same, in addition to this extra area, which you can see, that extra amount of heat gets rejected in a actual engine. And because of that, what happens? Work will not be maximum. This is the area of the work done. This part, I call it as irreversibility. Okay. W max is equal to QH minus QR. Area 1 to BA1 minus area 43 BA4. W actual is QH minus QL dash. QL dash is area 43 dash CA41. This is the heat rejected when the work is done is maximum. This is the heat rejected when the work done is actual. You take the difference of these two. Nothing but area 33 dash CB3, this area. This I can write it as T naught delta S net. Okay, this is the value I call it as irreversibility. Irreversibility I for the actual engine can be defined as the difference between the work for the reversible engine and the work of the actual engine. Yes. Here, why I have it reversible engine. Sometimes, okay, we'll write like this better. Exergy. The available energy is also known, that availability or available energy is also known as exergy. And unavailable energy is known as energy. So thus thermodynamics is study of energy, entropy and exergy. Let us find that maximum work. Reversible work is the maximum work that can be done by the system as it goes from the initial and final system states of a system are specified, assuming that the only heat transfer is with the surroundings. It is evident that this concept of reversible work involves both the first and second laws of thermodynamics. It is also evident that the work will be maximum only if the process is entirely reversible. Okay, you just consider this engine. Let us assume I have considered it as a steady flow system or a flow system. This is the mass entering into the system. This is the mass leaving the system. Okay, this is a system boundary or control volume, control surface, whatever you want, you can call it. The control surface. So work output. Here, heat is supplied to this reversibly. That's a very, very important. So irreversibilities are due to, entropy gets generated because of the temperature difference, that is external irreversibility, and also there will be internal irreversibility. We have to avoid both. So heat is supplied to this one, correct? Reversibly. So now let us find out what is the total work done is this work plus this work. So we call that W max is equal to W plus this WC. This is what I call it as work done by the reversible engine. Okay. So we'll find out this, we'll find out this, add both of them. So now the thing is, if the system is not steady flow type, that is the energy entering over here. So mass is entering. Along with that, it will have its enthalpy, kinetic energy, potential energy. Also, it will have its own entropy. Here mass is leaving. Again, it will have its kinetic energy, its enthalpy, its potential energy, its entropy. And you are getting some amount of energy might get stored. If this is greater than this one, may get stored. If this is less than this, so it may reduce. So that part is this. You please recall my explanation on steady flow energy, so that will help you there. Here only one thing I have shown here. I have shown a reversible engine. Delta Q naught heat is supplied, passes through the river, it rejects the heat delta Q and produces a reversible work delta WC. Total work output of the engine of this whole system is, I should take this plus this. Okay. Read this paragraph. Now let us look here. Referring to the diagram, delta Q. The heat is supplied reversibly. Mass entering into the system. Enthalpy of the mass that is entering into the system. Kinetic energy of the mass that is entering into the system. Potential energy of this. This is the work output of this. Energy leaving the system. As I said, this is stored. Energy stored. Okay. Since the process is reversible, the change in entropy of the system is, look here, delta Q by T, you have added heat, correct? You have added heat. So entropy of the system should increase. So that entropy is a reversible one, delta Q by T. And some mass is entering along with an entropy Si. That mass is leaving along with the entropy Se. This is because of the flow. This is because of heat addition to the system. And you know there is a reversible engine. It is taking an heat delta Q naught and rejecting an heat delta Q. This is the reversible engine's work. Okay, this and this you don't get confused. This is because of the flow rate and this is because of the reversible engine. And you know from absolute thermodynamic temperature scale I can write like this. Now you can play with it. So delta WC we can find out as I've already explained. So delta WC, delta T naught this delta Q by T, correct? Now T naught, this delta Q by T, we play with this from this. D is S sigma minus dmi Si minus this thing, and this minus delta Q. Okay. So the reversible work is the sum of the work done by the system and work done by the reversible. That is the maximum work. You can call this as delta W reversible or delta W maximum. Okay. This is by the system. This is by the reversible engine which supplies the heat to the system reversibly. So I know delta W equation from here. Then I know delta WC equation here. Substitute. Okay, this is the one. This I'll get it. Now reorganize. You will get this one. Correct. Now the question is, if it is steady, okay, steady, what will happen? This part will become 0 and integrate, this will become total work. W max is equal to mi. I like that, I can write. So this one. Okay, W reversible I can write. This, if you want, you call it as psi 1. This you want, you call it as psi 2. Is that correct? Yeah. No, I'm sorry. Avoid that. No. Let it be there like this. It's a closed system. Instead of enthalpy, you have internal energy. Correct. Again, mass is same. It is better you write this as m u1 minus u2 t naught s1 minus s2. That way we can write. Not a problem. So don't be under the mass is leaving. In a closed system, mass remains the same. Okay, right. So we have got this equation, that is W reversible or W maximum, whatever you want to call it, either reversible or maximum. In general, we'll define availability function H T naught S V squared by 2 GC G by GC Z. Okay, this is dead condition. H naught minus T naught S naught. If there is a potential head, if this is not there, that can be made 0. It means to say this is the condition. This is T naught, P naught, H naught, S naught, say Z naught. Right? Something entering at this condition. So entering at this condition, and this is H, this is S, this is V, this is Z. Right? So I can call this as H, S, V, So H T naught S V squared by 2 GC G by GZ H naught minus T naught S naught and G by GC Z naught. This part you can call it, you can define it as availability function. So then availability I means then you put HI, SI, VI, ZI like this. Then psi naught exit condition. Put this as HE, T naught SE, V, ZE. Okay. Finally, we can write HI, HE, subtracting one from the other. T naught SI minus SE, VI square minus VE square by 2 GC, ZI minus ZE, GC is equal to reversible. So you can say this is what the availability. And for a closed system, availability function we can define like this. Here instead of H, you will have, sorry, H you will have UI and UE, right? Okay, that's the maximum work. The reversible work. So the reversible work was considered for a change of state in which the only heat transfer was with the surroundings. This reversible work is maximum work that can be done during the given change of state. Okay, assuming that the only heat transfer is with the surroundings. Since every actual process has a reversibility associated with, the actual work W for a given change of state is always less than the corresponding reversible work W reversible. So this leads to a definition of the term irreversibility, which I have already defined. So reversible work correct. Then this is what we have done. Correct. Actual work, right. I am not considering steady flow or something. In general, I have taken. Actual work is this. So now the question is, I subtract one from the other, one from the other. The difference is, please observe here. Observe here. There is T naught SI here, T naught SE here. The T naught SI, T naught SE are not here in the actual work. If I subtract delta W from delta reversible, and I will get irreversibility. So delta is equal to T naught S2 minus S1 plus delta Q. Oh, this is for a closed system. This is for a flow system. This is exit entropy, inlet entropy plus delta Q. Here, to beginning of the state, beginning of the process, at state 1, end of the process, that is at state 2. So that's all the difference. This is how you can calculate the irreversibilities. Okay. Now let us talk about second law efficiency. First law efficiency we have done earlier. Efficiency is equal to 1 minus Q2 by Q1. Correct? That is first law efficiency. Assuming that W is equal to Q1 minus Q2. Now we are talking about efficiency based on second law. A common measure on energy use efficiency is the first law efficiency. The first law efficiency is defined as the ratio of the output energy of a device to the input energy of the device. Correct? The first law is concerned only with the quantities of energy and disregards the forms in which the energy exists. It does not also discriminate between the energies available at different temperatures. The second law of thermodynamics, which provides a means of assigning a quality index to energy, the concept of available energy and exergy provides a useful measure of energy quality. So you know that heat is a low grade and low quality, work is high grade, high quality, like this. So with this concept, it is possible to analyze means of minimizing the consumption of available energy to perform a given process, therefore ensuring the most efficient possible conversion of energy for the required task. For example, what we do is we use electrical energy, which is of high grade. Then we use this electrical energy for heating water to take bath. We are converting into low grade energy. This is what a high quality energy is aligned or matched with a low quality work. Suppose there is solar energy available, solar thermal energy available. I use this solar thermal energy for water heating. Then it is a good match. Okay, this high grade energy which is available for electricity, let us say I use to drive some mechanical device, maybe even a vehicle, then I am matching with a good task. So that is where exactly the second law efficiency comes into picture. The second law efficiency of a process is defined as the ratio of minimum available energy or exergy which must be consumed to do a task divided by the actual amount of energy consumed in performing the task. So what exactly it means is like this. Let us say you take coal, then you burn this, there is combustion efficiency. Then okay, then after burning this, you are transferring it to water to convert into steam. Correct? Boiler efficiency. Then you are talking about pipelines and other things. Okay, then will be losses. Next you are talking about turbine efficiency. Next you are talking about generator efficiency. Next you are talking about transmission efficiency. Finally it comes to user. Correct? Suppose if I 4 unit of coal, if I burn, the actual energy that comes to me here is equivalent to 1. And I use this energy for water heating. So this is what I'm wasting this kind of energy. So instead of minimizing the exergy, actually I'm maximizing the exergy. That is what exactly it should not be done like that. The second law efficiency process is defined as the ratio of minimum available energy which must be consumed. See, so much of energy. Like here, if at all my aim is to heat the water, directly I can boil the coal and I can heat this water. Correct? Then I will be minimizing that exergy. That is the thing. So minimizing exergy intake to perform the given task and actual energy intake to perform the same task. Actually, to heat this water of m kg with specific heat Cp to raise the temperature by, let us say, if 40 degrees Celsius or whatever it is. This is the energy required. This could have been done more efficiently by burning the coal directly. But you are following all these paths and finally you are converting a very high grade energy for heating. That is where the problem comes. Is it the most efficient way of doing this? So, actual energy intake. So you calculate all this kind of a thing, put that energy here, minimum exergy that is required. You can find out what is the second law efficiency. Okay, probably I could have this 4 unit means just with 1 unit of this energy I could have heated this, but actually I am using what, 4 units of energy. So that means I am simply this percentage 25% efficiency. I am not just matching this resource to the task. Okay, this is what we call the second efficiency. Let us look at what it means. Look at this. First law efficiency as I've already defined like this. Now this W I divide by W max reversible work. Again W max by Q1. What is W max by Q1? That is nothing but efficiency of the reversible engine, that is Carnot engine. This I am defining as second law efficiency. Okay, so now first law efficiency you have got. First law efficiency divided by Carnot efficiency, this becomes second law efficiency. Suppose first law efficiency is 0.7, Carnot efficiency is something 0.8, second law efficiency is 7 by 8. Okay, so the whole question is, now the question is, first law efficiency is, let us say 0.3, Carnot efficiency is 0.8, then it is 3 by 8. So second law efficiency is given by this equation. To improve second law efficiency, it is necessary that we need to improve the first law efficiency. This can be done by matching the source to task. With this we complete the discussion on availability, and we'll work out some example in the next session to understand this. Thank you.